Hello everyone, in this video we're going to go over the class note exercise for section 5.3. So first let's do some divisibility problems. So the first question here says, let's prove that 3 divides 2 times power to the 2 to the n minus 1. So as always, we're gonna say that this is our P of n. This is our property P of n that we want to prove. So we want to check the basis case. Since we're assuming that this is for n bigger than 0, then we gotta test that for n equals than 0 works. If n equals to 0 will mean that 3 divided 2 to the 0 minus 1, which is to say that 3 divided 0. Since this is true, 0 can be seen as 3 times 0. Okay, so we can verify that that is true. Now, for the hypothesis of induction, then for k that belongs to the integers, we have that 3 divides 2 to the 2k minus 1. Okay, that's going to be our hypothesis. Now we want to show that 3 divided 2 to the 2k plus 1 minus 1. Put this minus in the wrong place. So let's actually go and show it. So this is for 2 to the 2k plus 1 minus 1 can be seen as just 2 to the 2k plus 2, since that's what it is, and by properties of the power. So, but this is just 2 times 2 squared times 2 to the k minus 1. Notice that here, what I'm going to do is I want to be able to use the fact that we know that we can divide 2 to the 2 to the k. So we have this. And now at this point, I can just see, because 2 to the k, because by hypothesis of induction, 3 divided 2 to the k minus 1, that implies that 2 to the k minus 1 is equals to 3 times some m. This is for m that belongs to the integers. So that means that 2 to the k can be seen as 3m plus 1. So I can pretty much replace this in here. And from here, we can kind of go to being equals 4 times 3m plus 1 minus 1. If I simplify this a little bit, this is going to be 12m plus, and 4 by 1, 4, minus 1, 3. And so now notice that this is 12m plus 3, which I can factor the 3 and see it as 4m plus 1. So as you can see, this is divisible by 3. So 3 divided 2 to the 2k plus 1 minus 1. And P of n is true for n bigger than 0 by principle of mathematical induction. All right, so let's move from question now. We're going to get something similar, and all these strategies here are going to be very similar. So notice that now we change the numbers, but the strategy is pretty much the same. Here we have 8 divided 9 to the n minus 1. So it is very similar from the start. So the basic case, P of 0, is essentially saying what? That 8 divided 9 to the 0 minus 1. 9 to the 0 is 1, so this is just 8 divided 0. And we know that this is true because every number divides 0. 0 can be seen as a times 0. So this divide is 0. Now, we assume now for inductive hypothesis, the step 2, the inductive hypothesis, is that a divide is 9 to the k minus 1 for some k bigger than 0, right? So that's going to be that 9k minus 1 is going to be am for some m that belongs to the integers. Now, the step 3 will be to do the inductive step. So we essentially want to show that a divide is 9 to the k plus 1 minus 1. And so let's step 4, let's show it. 9 to the k plus 1 minus 1 can be seen, as you will expect, as 9 times 9 to the k minus 1. And now I can transform this 9 to the k into am plus 1. So from here, I can see 9 to the k as am plus 1 minus 1. And now this is 9 by 8 is 72 plus 9 minus 1, which is 8. And so as you can see, this is divisible by 8. This is just 8 times 9am plus 1. And so a divide is 9 to the k plus 1 minus 1. And so this will be the solution to that. And then we'll say, well, then by principle of mathematical induction, P of n is true for n bigger or equal than 0. Notice that when you're doing to do the proof, I have some reduced space here, but you should try to write everything that you need for the proof. Now let's go with question number 3. And question number 3 is 6 divided nq minus n. So I'm going to erase it around a little bit. So if you need to check something back, just backtrack on the video. Okay, so this is our P of n. So as always, basic case, step number 1, P of 1, since it starts from 1. 6 clearly divides 1 minus 1, since this is pretty much 6 divided 0. So in this case, it's going to work out. Once again, it's this k for the inductive hypothesis. It's this k so that 6 divided k cubed minus k. And so that implies that k cubed minus k can be seen as 6 times s for x that belongs to the integers. And now I want to show the end step, which is that 6 divided k plus 1 cubed minus k plus 1. And so let's show it. So first and then k plus 1 cubed minus k plus 1. So we have something that we can factor in here. But really, I can see this as k cubed plus 3k squared plus 3k plus 1. And so minus k minus 1, since this minus gets distributed, I get to cancel this 1. I get to subtract here. So this is going to be k squared minus k plus 3k squared plus 3k. Notice I can simplify this. And so, but I can just factor this out and see it as k cubed minus k, right? Which is my end. Sorry, this is not k squared, it's k cubed. This is my k step, k cubed minus k, right? And here for this one, I have 3k. So 3k common factor of k plus 1. So I have my p of k condition, which I can see as 6x plus 3k k plus 1, right? And so now notice that the product of k times k plus 1 is the product of two consecutive integers. So one of them gotta be even, right? So k times k plus 1, and this is something that we proved before, so that's why we're gonna use it, is gonna be 2j for some j that is belongs to the integers. And so this essentially is gonna be 6 times x plus 6 times some j. And so that shows that this is divisible by 6. So 6 divides k plus 1 cubed minus k plus 1. Okay, this hypothesis is very important. So this is something that you gotta write. The multiplication of a number by its next number, by his successor, is going to be a pair. Why? Because one of them, either k or k plus 1, is going to be even. So you got to be able to represent that in this form. Okay? But anyway, so we proved that 6 divides k plus 1 cubed minus k plus 1. So by principle of mathematical induction, we have that p of n is true for n bigger than 1. Okay? So here we're covering all this stuff. As you can see, we do some small steps that are needed to arrange and to extract the hypothesis of induction, which is the P of k. So when we break it down here, so we can extract the piece of the hypothesis of induction. You always that are proving, you need to do that. You need to make a way so you can extract the inductive step. All right, so now let's go for question 5. So here, I want to prove by mathematical induction that for all integers n bigger than 4, n factorial is bigger than 2 to the n. So let's prove the basic steps. So p of 4, 4 factorial is 24, and that is bigger than 2 to the 4, which is 16. So we're good. For some k now, the induction hypothesis, step number 2, for some k, in the integers, we have that k factorial is bigger than 2 to the k. Okay? Now, step 3, we want to show that k plus 1 factorial is bigger than 2 to the k plus 1. And so step number 4, let's show it. So we start from one side. So we're going to start from k plus 1 factorial. But of course, I have information on k factorial. So I'm going to see this as k plus 1 times k factorial. And so because k factorial is bigger than 2 to the k, then you can easily see that this is just going to be k factorial or k plus 1 bigger than k plus 1 2 to the k. Okay? And so here, now because k is bigger than, since k is bigger than 4, in particular is going to be, k plus 1 is going to be bigger than 5, which is going to be bigger than 2. And so I can see this as 2 times 2 to the k. And so that's just 2 to the k plus 1. So you can see here that we proved that k plus 1 factorial is bigger than 2 to the k plus 1, which is what we wanted to show. So by principle of mathematical induction, P of n is true for n bigger than 4. Okay, so we're going to stop here and we'll continue with the rest of the exercises in part 2.